All right, here is the first lecture of fluid mechanics. And we're going to really first define some basic fluid properties: density, specific weight, specific gravity, speed of sound, Mach number, and temperature. Some basic stuff that we currently use in fluids. Okay. First thing I want to do is define a fluid. It's a gas or a liquid. So it could be air, it could be water. Okay, so gas or liquid. Next one, density. We're going to get right to the stuff. This is a Greek letter rho, and it's equal to the mass over the volume. Okay, so mass, M over the volume. Units, kilograms per meter cubed in SI. And just to give you this, again, we have mass, volume, density. This is rho. Okay. It's the amount of mass per unit volume. All right, let's look at specific weight. Gamma. Gamma is the density times gravity. So the unit of density is kilograms per meter cubed. Unit of gravity, meters per second squared. Okay, so you could get a unit of kilogram over meter squared, second squared. This could also equal the weight per unit volume. So this is weight, and this is volume. Okay, just to give you an idea, usually we use this equation a lot, okay, because we have the density and we have gravity. Specific gravity, SG. SG equals the density of the fluid over the density of water, H2O, at 4 degrees C. Okay, and this is dimensionless, meaning that it's no unit. So it's just SG is, say, 2. Okay. And typically we use 1,000 kilogram per meter cubed for the density of water at 4 degrees C. All right. Let's change this to black. Let's look at temperature. There's actually 4 different scales. We have Kelvin, which is K. We have Rankine, which is R. We have degrees C, Celsius, and degree F, as in Fahrenheit. Okay, so let me write these. This is Kelvin, Rankine, Celsius, and Fahrenheit. And just to give you a few things, if you want to go to Fahrenheit to degrees C, you take 1.8, you multiply it by your temperature in Celsius, and you add 32 to get it into Fahrenheit. If you want to go to Kelvin to Celsius, TK of Kelvin, temperature in Kelvin, is the temperature in Celsius plus 273.15. Okay. We want to go to Rankine to Fahrenheit, degree Rankine, degree Fahrenheit plus 459.67, and say you want to go to Kelvin to Fahrenheit. Then degree Kelvin is temperature in Fahrenheit plus 459.67, all divided by 1.8. So just conversions. Now, Rankine and Kelvin are what we call absolute values. Okay. So we typically use those values in equations. So I can kind of go through. There's what we call an ideal gas equation, which is the pressure equals rho RT. Okay. This is pressure. This is density. This is what we call a constant. Depends on the gas. Okay. And this is temperature. So right now in my room or the room you're listening to, we know the pressure, we know the temperature, and we know it's air. We can find that constant in the back of your book. We can find the density of the air in there. Okay. And depending on the temperature and the pressure, the density or kind of the mass per unit volume, all right, will change. This is what we call the ideal gas equation. Okay. For example, say you have propane in a tank. It's pressurized. If you know the pressure, which you can see it on the gauge, you know the temperature kind of outside, you can find how well or how much mass per unit volume of that propane's in that tank. Okay. Which you can actually, if you know the volume, you can figure out the mass of the propane. Okay. Based on the density equations. Now there's a couple other ideal gas equations. P little v equals RT. This is what we call specific volume. And it's just the unit is, I'll show you, is your volume over your mass. So say your unit of volume is meter cubed, and this would be kilogram. Okay. So specific volume is meter cubed per kilogram. It's your volume per unit mass. So you can have specific volume, you can have specific enthalpy, other values, but we're not going to get into that right now. Okay. And then there should be one more that's commonly used, which basically I just changed density into mass over volume, and I brought the volume. So PV equals MRT. So you got 1, 2, 3 similar equations. Okay. And this is the ideal gas. This is only for gas that relates pressure, temperature, and density. Okay, let's just keep going. Some basic stuff here. Might be new, which is good, but a good basic information of fluids. Let's look at the speed of sound. I kind of like to give you some of these general, because you see it all the time. So we're going to use C as the speed of sound, and it's the square root of kRt, where T is your temperature in absolute. See how we did that? R, again, is your gas constant that I talked about before. And it's 287 joules per kilogram K for air. It's just a constant that you can find in the back of your book. And K is a constant as well. We're just going to leave it at that for now. And typically it's 1.4 for air. Okay, we're just starting fluids. We're just going to say it's a constant. Okay. So you can look at this and you can say, as the temperature gets colder, this goes down, your speed of sound will go down. Okay, pretty cool. Again, speed of sound is how fast sound waves propagate. Why do we use this? Why do we need to know that? Well, because you've probably heard the word Mach number. And Mach number is your velocity over the speed of sound. Okay, over the speed of sound. So if your Mach number is greater than 1, right, you're supersonic. You're going faster than the speed of sound. That when we're talking, right? Think about that. I'm talking. That wave is propagating and hitting you at the speed of sound. If Mach number is less than 1, we're subsonic. And if we'll just do this, m equals 1, we're sonic. And if m is greater than 5, we're hypersonic. Again, just some basic stuff. I believe homework 1, there's a graph that I want you to do that relates with Mach number. It gets you kind of kick-started in this fluid mechanics. All right, a couple other things. I'm going to do this one first. Let's look at weight and units. I kind of thrown some units in here previous. So W, I like to call weight, which is your mass times gravity, which could be units of pounds or newtons. Okay, so when you step on the scale, that's your weight. If you divide it by acceleration due to gravity, you'd get your mass. And G is 9.81 meters per second squared, or it's 32.2 feet per second squared. Okay, in English. Units are very, very important. Okay, every time you do a calculation, you need to put your units. So the unit of mass is kilogram. Unit of acceleration is meters per second squared. Okay. This is defined as a Newton. Oh. Okay. Or N. It's Newton. It's a force. It's weight. Okay. You have to make sure you're using SI and SI units. Okay. So if you're using English units, which is like feet, pound mass, okay, compared to SI, which could be which is kilograms, meters, second squared. Okay, you want to make sure you're using the correct units. Okay. All right. Just another thing. Let's look at Newton's second law. This will help on homework 1. Summation of the forces equals ma. Okay. Now, I put these vectors here because we know that, for example, say we have an inclined plane, and here's a box, that this could have x direction and y direction. That's why we have vectors, because those are forces along the x direction and the y direction, and could have acceleration in the x and in the y. Okay. Say this is going up and down, this incline, then acceleration in the y would be 0, right? So you could write some of the forces in the x equals max. Some of the forces in the y equals may. And this term you can say is 0, but there still are forces, right? You could still have your normal force. Here's your weight force, which acts straight down. And let's say the block is going upward. okay, you could have a friction force going downward because friction acts opposite. So what you need to do, again, if you remember, you need to break this W up into components. So you have WY, WX. Okay. And then you can write your forces down. For example, let's look at the X. We're going to assume this way is positive X and upward is positive Y. So we have negative friction minus WX equals MAX. Okay, we're going up the incline. Over here on the Y, we have normal force minus the weight in the Y equals 0. And let's say that this is theta here, which I believe this should also be theta. Then we could have minus friction minus W sine theta equals MAX. The normal minus W cosine theta equals 0. Okay, so over here, the normal force is actually a component of the weight force because you're at an incline. And here, your acceleration is a function of friction force and the component of the weight. If you remember from physics, friction, I'll put it right here, is fun. Okay? The friction force equals mu times the normal force. So we can rewrite that like this. And we now know the normal force, and you could plug that back into here, and eventually you can solve for AX. Okay? Now, this is the friction force of solid to solid. All right? You will know and learn when we get to viscosity, the friction force would be different if there is a liquid layer here. Okay? The friction force changes because the equation changes, and we'll get to that in viscosity. So, let's review, and let's go to the top, some of the basic concepts we're going to use. Understand fluid, it's a gas or a liquid. Density, which is mass over volume. Specific weight, which is gamma, that's the density times gravity. Specific gravity, which is the density over your substance divided by the density of water at 4 degrees C. We have 4 different temperature scales. 2 are absolute that are used in the equations. Kelvin, Rankine. Then you also have degree Celsius and degree Fahrenheit. We use these ideal gas equations quite often, which relates pressure, density, temperature. One equation is P equals rho RT. The next one is PV equals RT, where the little v is specific volume. And then we have the last one, which is PV equals MRT. Then we looked at the speed of sound, which is the square root of kRT, where temperature is T, R is a gas constant depending on the gas. Air has 287 joules per kilogram K. And then K is a constant. We're going to go right now, air is 1.4. If it was nitrogen or oxygen or whatever, or a mixture, you can find those values in the back of your book. We use the speed of sound to find Mach number, which is your velocity over the speed of sound. Make sure your important is units. You're using SI units or English units. Weight is a force. That's mass times gravity. That's the easiest way to remember a Newton, which is a force in SI. Then make sure, just a quick review from physics about Newton's second law. We have the sum of the forces equals ma. You could have x direction, y direction. You could also have the z direction, which would be in and out of the page. And you can break these forces into your components and write the x direction, the y direction, and you can solve for either acceleration, or if you know acceleration, maybe you need to solve for friction force or your weight force or whatever. Okay. Friction force equation is fun. And just to remember, if you have a liquid between your two surfaces, that creates a different friction force. That creates a different friction force, and you need to account for that. All right, I hope this is a good start on some basic stuff. If you have questions, let me know. Thank you, and bye now.